All right, so today we're going to be talking about the quantum wave mechanical model of the atom. Um, it was developed by a guy named Erwin Schrodinger. Note that at this time period in physics, it was really interesting because they were sort of developing new insights and sort of trying to develop their understanding of the world with those new insights. So at this point, it was postulated that light was both a wave and a particle. So some other smart people, like Erwin Schrodinger, I think is how you say it, um, tried to apply this same sort of principle to electrons, that they are waves. So what he did is he treated them like a standing wave and created what we call the wave function through his series of equations called the Schrodinger equations. And when you square them, you get probability functions. And what you end up getting are orbitals, which are mathematically defined regions of space where you have a certain probability of finding an electron. Um, this is what the 1s orbital of hydrogen looks. This is what the hydrogen's wave function looks like, and this is what we call the 1s orbital. Um, we can firstly, when we talk about this sort of this model, we have to go back to talking about main energy levels or principal energy levels. So there are main energy levels that go 1, 2, 3, so on. So energy level 1, energy level 2, 3, so on and so forth. And they can hold a different number of electrons. They each hold a different number. They each hold a different amount of electrons. And the way we can quantify this is that it's given by the formula 2 times n squared, where n is the principal quantum number, which denotes the energy level you're talking about. So as you go further and further away from the nucleus, just think there's more electrons there, so they have more repulsion, and hence they get further and further away, and therefore there are more electrons there in that given space. When we go on to topic 3, that might make a bit more sense, but for now, you'll just take my word for it. So each main energy level beyond n equals 1 is made up of different types of sublevels. So the levels themselves are divided into sublevels, and going from lowest to highest energy, they are S, P, D, and F. So here's sort of an energy level diagram sort of denoting that. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, and so on. As you can see here is that generally S, P, D, F, that's the order in which the energy levels, the energy sublevels go in. And as you can see here, energy level 2 has more energy than 1, and so on here. This is increasing energy, and so on and so forth. Orbitals are defined as a mathematical, as we already said. Um, each main energy level, the reason they can hold more electrons is that they can hold more orbitals since they're bigger. They can hold more orbitals, and each orbital holds exactly 2 electrons. And the sublevels, they are further and further away from the nucleus, and they can also hold more electrons. Excuse me. So the S one holds 1 orbital, the P sublevel holds 3 orbitals, the D has 5 orbitals, and the F has 7 orbitals. So, and then if you want to get the number of electrons total that they can hold, you just multiply the number of orbitals times 2, because there's 2 electrons per orbital, and if you have 3 orbitals, there are 6 electrons total in the P sublevel anyway. Shapes of S and P orbitals. S are pretty obvious. They look like a sphere, and the P orbitals, since there's 3 of them, there's 1 on each axis. So, and they look like a dumbbell. So you have a dumbbell on the x-axis, the y-axis, and the z-axis. And then when we add electrons to atoms, they must follow 3 quantum mechanical rules: the Aufbau Principle, Hund's rule, and the Pauli exclusion principle. The Aufbau Principle states that as atoms are built up conceptually and protons are added to the nucleus, electrons are added to the beginning of each orbital, beginning at the lowest energy orbital, blah blah blah. Basically, it's saying you cannot fill any. You have to fill the lowest energy orbitals first before filling up the highest energy ones. So you fill them up in increasing order, more or less. Hund's rule is basically states when assigning electrons to orbitals with the same energy, keep them unpaired as much as possible. Just keep your electrons unpaired. And the reason for this is quite simple. Electrons, they are negative charges, so two negative charges will repel. So keep them far apart and they won't repel. Pretty simple. The Pauli exclusion principle states that no two electrons may have the same quantum state, and to fully describe the quantum state, you need the main energy level, the sublevel, the orbital, and then the spin. Basically, if you have to pair electrons, keep them with opposite spin. Here we have an energy level diagram, which you may have to draw. So let's switch over to this screen and actually draw an energy level diagram out for you. So I'm going to do carbon because it's easy to do. So energy on the y-axis here. So here we have 1s, and then we have 2s, and then we have 2p. So carbon has 6 electrons, so 6 electrons. I'll keep a tab of that there. So according to the Aufbau principle, we must fill this one first. So notice how they have the opposite spin states. You could just use an arrow to indicate spin up and spin down, right? So there's 4 electrons. Then we have to fill the 2s orbitals, so one up, one down. And then lastly, we fill the p orbital. And note here that the electrons must be, well, as far apart as possible. So, but these are on different axes, so it doesn't matter. So we'll fill it like that. So according to Hund's rule, these must be unpaired, whereas these ones had to be paired because Aufbau's rule is the Aufbau principle is number 1, and then Hund's rule is 2, and then the Pauli exclusion principle is 3rd. Generally is how it works. So the Aufbau principle takes precedent over the other rules, with very few exceptions, but they exist because quantum mechanics is not perfect, or at least at this level. So yeah, I think that's it. Alright, for core, lastly, I want to talk about core and valence electrons. Noble gas electron configurations are by far the most stable electron configurations because all the orbitals are full, and so are the energy levels. So it doesn't want to change that. So valence electrons are the electrons that are on the highest main energy level of an atom, and they determine the chemical properties of that element. So for example, if the main energy level is almost full, then it'll want to just fill it up the full way there rather than give up. Whereas if there's hardly any electrons there, it'll just want to kind of get rid of them, so it doesn't have to have them. When we do topic 3 and 4, this makes a lot more sense, but for now, you'll just sort of have to go with me here. So the number of valence electrons related to the group number in the periodic table. For groups 1 to 10, it's just the number you went down. So group 1 elements always have 1 valence electron, groups 2 always have 2, groups 3 3, and so on and so forth. Once you get to 10, it's just when you get to group 13, it's this subtract 10 is the number of valence electrons it has, with the exception here of these ones. They really don't have valence electrons since they're full. I don't know. They are counted as having 8, so yeah, we'll do it like that. And then lastly, we can write what is called an electron configuration, which is basically sort of what we did here, but in a more written form. So here it's just 1s, so main energy level, sublevel, and then in the exponent we have the number of electrons. We write that sort of as a superscript. We write the number of electrons in that orbital as a superscript, and then we do 2s2, 2p2. Yeah, that's the electron configuration for carbon. And with that, I think that's everything. Thank you. Thank you very much for watching. See you next time.